Okay, I hope I'm audible to all students who are attending this lecture of Mathematical Methods for Economics, Part 2. We continue with our lectures on functions in several variables. This is the broad topic for our lectures. Formally, this is chapter 15 of the book I prefer to follow for the MME2 course, which is Sydsaeter and Hammond. The fourth edition of this book. Now, all students can recall that in the previous lecture based on functions in several variables, we had done the concept of level curves in the three-dimensional space. Okay, we had also done a few problems from section 15.1 of Sydsaeter Hammond. Okay, so now in this particular lecture, we intend to start with a new topic within functions in several variables. This is called partial derivatives. Partial derivatives with two variables. This is a new subtopic within our broad lectures on functions in several variables. Partial derivatives with two variables. Now, all students can recall that in my Mathematical Methods for Economics Part 1 course, when we had y as a function of x, in the MME1 course, we had y as a function of x and dy by dx is the first order derivative. Dy by dx is defined as the first order derivative of the variable y with respect to the variable x. Okay, this was what we had done in the Mathematical Methods for Economics Part 1 course when we had done single variable optimization. Okay, now what changes in this particular topic? So now z is a function of two variables x and y. Then define del z by del x. You can see now the sign has changed. It's not d, it's del. Del z by del x as the partial derivative of z with respect to the variable x when y is held constant. So del z by del x is the partial derivative of z with respect to the variable x when y is held constant. And similarly, I can say define del z by del y as the partial derivative of z with respect to y when the variable x is held constant. So when we talk about del z by del x, it means we are partially differentiating z with respect to x when y is kept constant. And when we talk about del z by del y, we are partially differentiating z with respect to y, keeping x constant. Okay, so now we can use the following notations. So when z is now a function of x and y, I can use the following notations which will be used again and again. Different books will be using different notations. So I can say partial derivative of z with respect to x is denoted by, I can write it as del z by del x. I can also write it as derivative of the function with respect to x, del f by del x, or some of the books write it as zx. Zx means z subscript x means del z by del x, or some of the books write it as fx, or some of the books even write it as f1. F1 is treating x as variable 1 and y as variable 2. So when you will refer to different books for mathematical economics, you will see different notations. I have written all possible notations. Some of the notations you will find them in Sydsaeter Hammond. Some of the notations you will find them in Mathematics for Economics by R.S. Bhardwaj. One of these notations you will find in Mathematical Economics by Alpha Chiang. So all are the same. When I talk about partial derivative of z with respect to x, I can write it as del z by del x, or del f by del x, or zx, or fx, or f1. They all describe the same term. Similarly, just for completeness, I can write similarly partial derivative of z with respect to the variable y is denoted by del z by del y, or del f by del y, or zy, or fy, or f2. So again, all these terms are the same. They depict the same term. Okay, so I hope so far it's clear. Now let us actually practice questions on how to partially differentiate. So if I erase this off, let us look at a few practice questions based on partial differentiation. Now you are going to follow the same rules which we had learned in the mathematical methods for economics course. All of us know the power rule for differentiation, the product rule of differentiation, the quotient rule of differentiation. Okay, so keeping all those rules in mind, which we had done in the mathematical methods for economics part 1 course, we are going to use the same rules to now compute the derivatives of the following functions. So question number 1, given f of xy as x cube y plus x square y square plus x plus y square, find del f by del x and del f by del y. Okay, so we are given the function, consider f of xy is given to us. Now, how do I find out del f by del x? I will be differentiating the function with respect to x, assuming that y is a constant. When you are partially differentiating with respect to x, you assume that y is a constant. Okay, so what is the derivative of x cube y with respect to x? Y is a constant. X cube ka derivative is 3x square times y, plus y square is a constant times x square ka derivative is 2x. X ka derivative is 1. Y square ka derivative is 0. Why? Because y is assumed as a constant. So what is my answer? Del f by del x is 3x square y plus 2xy square plus 2. Similarly, we can quickly find the partial derivative with respect to y. So del f by del y. Now you will differentiate f with respect to y, assuming that x is a constant. So x cube into y ka derivative 1 plus x square into y square ka derivative is 2y plus x का derivative is 0 because x is a constant. Y square का derivative is 2y. So therefore my del f by del y comes out as x cube plus 2x square y plus 2y. So hoping all students have understood this question and have no doubts. Let's look at the second question now. Okay, given f of xy equal to xy upon x square plus y square. Again, the question asks compute del f by del x and del f by del y. Let's solve this. We are now going to apply the question rule. Okay, all students can recall if f of x is equal to u of x by v of x, then the question rule tells us f dash x is equal to denominator into numerator का derivative minus numerator function into denominator function का derivative upon denominator function का square. This is the very famous question rule in differentiation. Let's apply it to this question. If I have to find del f by del x, treat y as a constant. Denominator into numerator का derivative minus numerator into denominator का derivative upon denominator का square comes out as x square y plus y cube minus 2x square y upon x square plus y square का square. So I can say my del f by del x is y cube, x square y minus 2x square y is minus x square y upon x square plus y square का square. Okay, and on similar lines we can quickly find out del f by del y. So for that I am erasing the question rule now because all students know this rule by now. So if I now find del f by del y, it's going to be denominator into numerator का derivative minus numerator into denominator का derivative upon denominator square. And if you work it out, you can check it comes out as x cube minus xy square. After doing some algebra, it comes out as this upon denominator ka square. Okay, so this is our del f by del x and del f by del y. Okay, so hoping students have understood these two practice questions where we have learned how to partially differentiate the function with respect to the variables x and y. Now let's move on to higher order partial derivatives. Higher order partial derivatives. Okay, so if z is a function of x and y, then del f del z by del x, or I can write del f by del x and del f by del y are called the first order partial derivatives. They are called the first order partial derivatives. Okay, and these partial derivatives themselves are functions of two variables. These partial derivatives themselves are functions of two variables x and y. That is, I can say that del f by del x itself is a function of x and y, and del f by del y itself is a function of x and y. So now therefore define the second order partial derivatives. Define the second order partial derivatives of f of xy as, so the second order partial derivatives are, so del f by del x if I again differentiate it with respect to x. Del f by del x if I again partially differentiate it with respect to x, what do I get? Del square f by del x square. Del f by del x, del f by del x if I differentiate with respect to y, I get del square f upon del y del x. Then third, del f by del y if I differentiate with respect to y, del square f by del y square. And the fourth one I am writing on the top, erasing the initial part. So the fourth one, del f by del y if I partially differentiate with respect to x, I get del square f upon del x del y. Now this derivative and this derivative are called the direct second order derivatives. Okay, so I can say these are called the, I can write it here. Let me erase all of this off and I can write it. So a note as follows. Okay, del square f by del x square and del square f by del y square are called, they are called the direct second order partial derivatives. These are called the direct second order partial derivatives. And if I talk about del square f by del x del y and del square f by del y del x, these are called cross second order partial derivatives. These are called cross second order partial derivatives. Okay, now all students should be knowing the notations of these, how to denote these. So we can write the notations, which you can find in different books. So del square f by del x square, you can also write it as fxx. You can also write it as f11. And you can also write it as del square z by del x square, assuming that z is a function of x and y. Similarly, del square f by del y square, you can write as fyy. You can also write it as f22. You can also write it as del square z by del y square, assuming that again z is a function of x and y. Third is del square f by del y del x. You can write it as fxy. That means first you are differentiating with respect to x, and then you are again differentiating but with respect to y. So this I can write as f12. This I can write as del square z by del y del x. Again, assuming that z is a function of x and y. And then we can have the fourth notation, for which I am just erasing the initial part. We can now have the fourth notation, which I am putting up on the screen. This is del square f by del x del y. This is nothing but first you are differentiating with respect to y, and then you are partially differentiating with respect to x. So fyx, which is nothing but f21, which you can also write as del square z by del x del y, assuming that z is a function of x and y. So now you open up any book relating to mathematical economics. These are the standard notations we use. Some books are going to use some notations, other books are going to use other notations. You should be familiar with all the classical notations which are used in standard books for mathematical economics. Okay, now after we are done with the notations, we can now look at practice questions based on second order partial derivatives. So practice questions based on the second order partial derivatives. So let's look at these questions. Question 1. Compute all second order partial derivatives of the function f of xy equals x cube y plus x square y square plus x plus y square. I have taken the same function which we have taken before in our lecture. Okay, so let's find all the second order partial derivatives as follows. So first of all, del f by del x will be differentiate the expression with respect to x, keeping y constant. 3x square y plus 2xy square plus 1. And let's quickly find out del f by del y also. It's going to be x cube plus 2x square y plus 2y. Okay, now from these first order partial derivatives, we can find all the second order partial derivatives. Del square f by del x square will be differentiate del f by del x again with respect to x, 6xy plus 2y square. Then del square f by del y del x will be differentiate del f by del x but with respect to y. You get 3x square plus 4xy. Now let's find del square f by del y square. Differentiate del f by del y with respect to y further. What do we get? We get 2x square plus 2 and del square f by del x del y would be the partial derivative of del f by del y with respect to x. Comes out as 3x square plus 4xy. Now, do you observe something? You would see that del square f by del y del x is exactly equal to del square f by del x del y. What does this mean? It means if you first partially differentiate the function with respect to x and then differentiate with respect to y, or if you first differentiate the function partially with respect to y and then with respect to x, you will get the same answer. So this theorem in mathematical economics is called as the Young's theorem. That's the next heading for all students. Okay, so I'm writing the statement of the Young's theorem. Suppose I write that z is a function of x and y, then Young's theorem states that if you differentiate the function with respect to x and then differentiate with respect to y, it will exactly be equal to the derivative of the function first with respect to y and then with respect to x. Okay, so assuming that both the above partial derivatives, are continuous. So this is the statement of the Young's theorem. Young's theorem simply states that if you first differentiate the function with respect to x and then with respect to y, and then you switch and you first differentiate with respect to y and then with respect to x, your answer is going to come out the same. Okay, so now let's practice a question based on Young's theorem. So our heading now is practice question based on Young's theorem. So let's look at this practice question. If the function f of xy is x cube e to the power y square, find the first and the second order partial derivatives at x comma y particularly equal to 1 comma 0. Also verify Young's theorem. So let's quickly solve this. We are given the function f of xy is x cube e to the power y square. Let's quickly find out all the derivatives. So students, now I'm using short forms because they are much easier to work with. So I prefer to use fx, fy and so on. So fx will be partial derivative of the function with respect to x, which is 3x square e to the power y square. Fy will be partial derivative of the function with respect to y, which is x cube into e to the power y square into derivative of y square is 2y, which is 2x cube y e to the power y square. Then fxx will be differentiate fx again with respect to y, so it's 6x e to the power y square. Fyy will be differentiate fy again with respect to y, so it's 2x cube times, we can apply the product rule with this term and this term, so y into e to the power y square into 2y plus e to the power y square into y ka derivative is 1. So my fyy comes out as 2x cube times 2y square e to the power y square plus e to the power y square. Now we can quickly find out fxy. Fxy is that fx function you are differentiating with respect to y. So 3x square into e to the power y square times 2y, which is 6x square y e to the power y square. And then fyx will be, fy is getting differentiated with respect to x. So it's going to be 6x square y e to the power y square. So clearly all students can see that fxy is exactly equal to fyx. The two are exactly the same. Now all I have to do is to evaluate all these derivatives at 1 comma 0. So we can quickly do that. For that I am erasing the initial part now. I am even erasing the question. Just put 1 comma 0 in all these derivatives, you get the required answer. So fx at 0 comma 1, fx at 0, 1 would come out as 3 into 0 ka square at 1, 0. Let me correct myself. Fx at 1, 0. The question, the x and y coordinates are 1, 0. Okay. So fx at 1, 0 will be 3 times 1 ka square e to the power 0, which is 3. Fy at 1, 0 will be 2 times 1 ka cube into 0 e to the power 0 square, which is 0. Okay. Then we have fxx at 1, 0. Put 1, 0 here, so we get 6 into 1 into e to the power 0, which is 6. Fyy at 1, 0 will be, put 1, 0 in this, so we get 2 times 1 ka cube into 2 into 0 ka square e to the power 0 plus e to the power 0. So this is 2 times 0 plus 1, which is 2. Okay, then fxy at 1, 0 will be 6 times 1 ka square 0 e to the power 0, which is 0. And fyx at 1, 0 will be, again, it's going to be the same by Young's theorem. So these are our answers for this question. Okay, and now let's look at one more question and then we stop. Question 2. Consider the function x equal to a p to the power minus 1.5 r to the power 2.0. The question asks us compute del x by del p and del x by del r and discuss their signs. Given that a, p and r are all greater than 0. This is a very easy question. X is given to us as this. What will del x by del p be? Differentiate partially with respect to p, keeping r constant. This is going to be minus 1.5 a p to the power minus 2.5 r to the power 2.08. You can see a is positive, p is positive, r is positive, but there is a minus sign outside, so the whole term is negative. And similarly, quickly do del x by del r, so it's going to be 2.08 a p to the power minus 1.5 r to the power 2.08 minus 1, which comes out as 2.08 a p to the power minus 1.5 r to the power 1.08. This is positive, this is positive, this is positive, this is positive, whole term is positive. So for this question, del x by del p is negative and del x by del r is positive. So this is where I intend to stop in this particular lecture. Objective of this lecture was to introduce to all students how to find the first order partial derivatives and second order partial derivatives of the function z as a function of x and y. So I hope all students have enjoyed this lecture. Any doubt, you can unmute your mic and ask, or call up or mail me your doubts at divineschoolofeconomics@gmail.com. So this is where I stop in this lecture.